Hello everyone. It is already 6:10. Let's start our today's discussion. So first of all, I introduce myself. My name is Rajat Bonik. Uh, my name is Rajat Bonik. I am from IITISM Dharmad. I am one of the PML research scholar at IITISM Dhanbad and also taking this ground improvement lecture class as a TA of Professor Dilip Kumar Vaidya sir, who already taught this course at NPTL. Uh, so I am this class is discussion class of this week 11, and this is today we discussing first we discussing the lectures which in this weeks, and then if time permits, uh, I will discuss some problems and also previous year assignment question, and also this session is recorded. So after this session, this video will be uploaded at my YouTube channel. You can access through NPTL, and also whatever I am discussing in this session, uh, all this material will be shared by Google Drive. So don't worry about this. We have only left two classes of these lectures, ground improvement lectures, and today is 11th week, and today I am discussing the geosynthetics and geometry of technique, uh, ground improvement technique. So I am sharing my PPT. Please keep patient, and I am sharing my presentation. So today I am discussing the one of the ground improvement technique. This is called geosynthetics, and by this technique we can improve uh, the ground by many different way, and to also to handle the also the handle the soil and improve the different properties of the soil and function, and by this technique, and it is very cheap technique, uh, and in this technique we use some polymer or synthetic material, and along with using this synthetic material with soil, after by combining these two, soil and this synthetic material, we improving the ground, and we address different function or weakness of this ground by this way. So let's start from first slide. So here it is. It is said that geosynthetic material, a planar product manufactured from polymeric material used within geomaterials to enhance the geotechnical engineering or geostructural properties through reinforcement or and improvement. So geosynthetic material is a polymeric material. It is uh, that means it is one polymeric like PVC or some like plastic, which is by polymerization this product is produced. Then it is used in geomaterial, that's well, and improving the geotechnical and also geostructural properties like shear strength, bending moment, also geostructural properties, uh, drainage, filtration of the soil, and also act as a reinforcement. and by this way improving the ground. Geosynthetic is a generic term for all synthetic material used in geotechnical engineering application, including geotextile, geogrid, geomembrane, geocells, geocomposites, and geonet. So geo means geomaterial, or we can say ground or soil, and this when this geomaterial you is apply with some synthetic material like polymer, plastic, or PVC, polyvinyl chloride, then this combine we call geosynthetic material. And there are different application of the geosynthetic material, like we can use this material as a geotextile, as a geogrid, geomembrane, as a geocell, geocomposite, and geonet. We one on we discuss of these different types of geosynthetic material. Then there is types of geosynthetic material. So here it is given. There are different types of geosynthetic material. It is geogrid, geotextile, geonet, geocomposites, geomembrane, geosynthetic clay liner, geocellular confinement system, geomers, geopipes, and geofoam. And these are the different techniques we use, or sorry, these are different types we use in to improve the ground by geosynthetic material. Hello, sorry for that, and there is some technical glitch. So, sorry for that. We discussing the different types of geosynthetic. So first one is here it is geogrid. I think my voice and video is clear. So first one is here geogrid. So geogrid, a geosynthetic formed by a regular network of the apertures typically used for reinforcement purpose. So here some figures is given of different types of geogrid. So first one it is triaxial geogrid, then biaxial geogrid, then welded geogrid. So these are the different types of geogrid. So this geogrid mainly used for reinforcing of the soil. We know that soil is strong for taking compression load, but it is weak in tension. So for there we uh, so for increasing the tensile strength of the soil, we use this geogrid, and by reinforcing the soil, by reinforcing, we increase the tensile strength. Then we discuss about the geotextile. It is like cloth. It is look like a cloth. So a geotextile or geofabric is a permeable textile used with foundation, soil, rock, earth, or any other geotechnical engineering related material as an integral part of a human-made project structural system. So it is this type of geosynthetic material like that means geotextile or also called geofabric. It is look like a cloth or cloths of so it is permeable in nature and it is mainly used to for drainage or filtration purpose and or sometimes used for separation purpose with some human-made project like dam, road, foundations like that. Then another one is geonets. Another type is geonets. So geonets are made of stacked crisscross polymer strands that provide in-plane drainage. Nearly all geonets are made of polythene. So if we see in figure that these are made with some polymer strand with crisscrossing and it mostly provided for mostly used for the in-plane drainage. In-plane drainage that means soil can pass in between these geonets. So and this is mainly made of polythene. The polythene polymer is used to made of this geonets. And there is two type of geonets is given here. One is biplanar, another one is triplanar. And then another type is geocomposites. So these are products manufactured by combining the superior features of various types of geosynthetics. And the object is to produce material which are multifunctional and are faster to install than the individual components. So these composites mean combining two or more types of geosynthetic material and produce a new type of material or new function of new designing of material, geosynthetic material. And this is mainly used for multifunctional work and also you easy or faster to install than the individual component. Uh, we- so these are the properties of this geocomposite material. Then geomembrane. So geomembranes are relatively impermeable sheet of plastic. So this geomembrane mostly used for the separate of two liquids or we can say separation of use in waste management to separate the waste material from the ground or we can say infiltration of waste material or liquid into the ground we can prevent it by this applying this geomembrane. Then another one is geosynthetic clay liner. Geosynthetic clay liners include a thin layer of ground bentonite clay. When wetted, the clay swells and becomes a very effective hydraulic barrier. And geosynthetic clay layer are manufactured by sandwiching the bentonite within a or layering it on geotextile or geomembranes, bonding the layers with needling, stitching, or chemically adhesive. So we know that clay is soiling nature. It has soiling nature. So when it is wetted, clay soil, that means volume increase. Due to the increase of volume of clay, this clay actually we know that clay is impermeable material also. So this clay is act as a hydraulic barrier in between this soil. So and it this is made by sandwiching technique. That means in between two geotextile we apply bentonite type of clay. So by this way, we can make geosynthetic clay liner. Then geocellular confinement system. Geocellular confinement system are three-dimensional honeycomb-like structure filled with soil and concrete. Geocellular uh, confinement system are often called the geocell, is made of a strip of polymer or geotextile connected at staggered point so that when the strips are pulled apart, a large honeycomb mat is formed. So the honeycomb, we see that uh, uh, in soil also, in composition of soil also, we see that soil particle is one of the structure of the soil particle is honeycomb structure. So same way we can arrange this geotextile or geo strip of geopolymer in honeycomb structure, and we formed a geocell uh, type of structure. And in between this cell, we fill this cell with the soil, rock, or concrete. And and, and this act as a whole, as act as a solid material, and it is uh, give very good strength like that way. Then geomats. Geomat is a three-dimensional erosion control mat consisting of a UV stabilizing lev labyrinth-like extruded polymer core mounted on a rough knitted mesh. So these are the material used to create these geomats. So geomats mostly used to control the erosion, and it is three-dimensional, 3D in nature. You can see in figure also. It is three-dimensional a mat and mostly used for control the erosion. Geomats acts in three major mechanisms. These are surface reinforcement and confinement of the soil, protection against raindrops, and reinforcement of the slope, and at the same time allowing vegetation grass growth. So these are the three major functions of geomats. That means you use as a surface reinforcement, protect the raindrops, protection from the raindrops, and also as a reinforcement of slope. Then we come to geopipe, and another significant product which has been adopted as a geosynthetic is a plastic pipe. There is a wide variety of civil engineering application of this product, including highway and railway edge drains, in interceptor drains, and leachate removal leachate removal system. So this geopipes is used at the ground for drainaging purpose, mostly for drainaging purpose. And these are wide range of there are wide range of application of this geopipe, and it is mostly used for highway and railway for as drainages purpose. Then geofoam. Geofoam is manufactured into large block which are stacked to form a lightweight, thermally insulating mass buried within a soil or pavement structure. So geofoam also a 3D nature, 3D type structure. Uh, it is mostly used as a thermal insulator, and also it has lightweight and mostly used to confine on the soil for pavement or embankment purpose. Typical application of geoform includes within soil embankments built over soft, weak soil, uh, under roads, airfield pavements, and railway tracks systems subjected to excessive freezing through condition. Beneath on grey storage tank containing the cold liquid. So we know that these geoforms act as a thermal insulator. So it is mostly used to as a underground to keep the temperature constant. So most of the time it is used as for the storage tank containing cold beneath the storage tank controlling containing the cold liquids and also as a cold weather area for control the freezing and throw action in embankments, road embankments. Now, different types of different function of geosynthetic material. So, how many ways we can use this type of synthetic material? We now discuss, or we can say, what are the different function of this geosynthetic material? One by one, we discuss now. So here it is. First one is we use as a reinforcement material. Then also you can use this geosynthetic material as a filtration purpose, and then as a separation purpose also, drainage purpose also we can use, and also control the erosion we use, or barrier and protection purpose also can use. And these are the common function of the geosynthetic material. So one by one we now discuss this function. So first one is here it is reinforcement. Reinforcement that means geosynthetic material used as a reinforcement. So reduction of stress intensity through distribution of the stress over the wider area. Then that means when we use this geosynthetic material as a reinforcement, we can actually increase the load distribution area. Uh, or and by that way we reduce the stress intensity or concentration of stress. You can see the figure also, see in the figure also that if without synthetic material, the load is as a reinforcement without as a reinforcement, the load is concentrated in one place. But when we applying the geosynthetic material as a reinforcement, this geosynthetic material is distributed the load over a wide area. So by this way, we can avoid the failure which is caused by the concentrated load, and or localized failure we can also avoid. So these are one of its this is one of its function. Then there are other discussion of this uh, function, that is geosynthetics provide reinforcement effect through three possible mechanisms. That means lateral restraints of the base and subgrade through friction and interlock between the aggregate soil and the geosynthetic. Increase in the system bearing capacity by forcing the potential bearing capacity failure surface to develop along alternate higher shear strength surface. And then last one is membrane support of the wheel load. So we can see in the figure also this geosynthetic material, first one for the use reinforcement use as a lateral resistance due to friction. So in friction between, that means friction and interlocking properties are used when we can apply this geosynthetic material as a reinforcement, and by this way we can increase the strength also. And also this geosynthetic material also increase when we apply use as a reinforcement, it is increase the bearing capacity also by developing this failure surface at a greater depth. And also as a vertical membrane, we can use this geosynthetic material due to wheel loads. So these are the three different mechanisms we mostly use uh, for which this reinforcement, geosynthetic as a reinforcement mostly use. Then we come to separation, geosynthetic material as a separation. So preventing intermixing of soil soil or aggregate to maintain the integrity of each material, yet still allow the free passage of liquid gas. Commonly used in between the subbase, subgrade, and around drainage material. So actually, we can use this geosynthetic material separator to separate the coarse grains and fine grained soil, and also we use this type of material uh, as a as a uh, as a way that it can allow also free passage of methane gas. So you can see that figure, the function of geosynthetic with geosynthetic material as a separator, but in the second figure there is no geosynthetic material as a separator. So intermixing of the particles, that means a coarse segregated fine segregated are intermixing to each other, and in second figure, and by this way the above pavement uh, get failed. So the contamination of the base course layer leads to the reduction of the strength, stiffness, and drainage characteristic, promoting discharge and early failure of the roadway. So by this way, if we can if we do not use this geosynthetic material separation, then base course may fail due to the reduction of the strength, stiffness, and also the drainage characteristic also decrease, and road may get failed. Sorry. And then geosynthetic material as a filtration. The geosynthetic material we can use as a filtration. So rest, restraining soil particles subjected to hydraulic force, which least allowing the passage of liquid gases. This function is often part, partnered with separation. That means this geosynthetic material, when we use as a filtration, this can also use as a separation also. That means we separate the uh, sorry, we actually in this function we actually uh, filtered the water. That means we can restrict the flow of the particle with the water, and only passes the water only, or gas only. And it is mostly used for in the pavement work when it is used as a embankment. When you construct embankment, and there is a possibility to flow. There is possibility of uh, particle flow with water, and to confine this particle and only pass the water, we can use geosynthetic as a filtration. So you can see the figure also. This one pavement is here, and below the pavement there is one permeable layer, and then we can use textile material as a filtration with in between two just textile material. We use some good drainage material, that means gravel aggregate, and also one perforated pipes also put into it. And if or there is a rainy season if water flow below the ground surface, and that can easily filter by this geosynthetic material, and water can uh, give way with this perforated pipe. And by this arrangement, we can use geosynthetic as a filtration. Now we can also use geosynthetic as a drainage. One thing is remember that when we use geosynthetic material as a filtration, uh, then cross-plane drainage may take place. That means the drainage of water is take place through the cross-section of the uh, uh, through the or we can say perpendicular to the geosynthetic material. But when we use geosynthetic material as a drainage purpose, then in-plane drainage may take place. That means water can flow in between the geosynthetic material, and by this way we can drain out the water, excess water. So in drainage, allowing fluids and gas to flow both through the plane of the material, commonly used as a component in geocomposite used for surface water runoff or for gas collection under the membrane. So it is mostly used the geosynthetic material as a drainage to collect the surface water as a runoff, and also collect the gas under the membrane. So and mostly used for in dam, uh, earthen dam. Mm, uh, and we know that there is maybe seepage in between the dam. So to prevent the seepage, we can use this geosynthetic material as a drainage to remove the excess water in between the dam, and we can um, increase the strength of the dam. So one arrangement is given here as a drainage. We can see that same arrangement as for filtration also, but uh, in drainage, this is used as a in plane. Water can flow in plane. So by this arrangement, water is out, or excess water is expel out from this soil and increase the strength of the soil. Now, geosynthetic characteristic influencing filter, separation, and drainage function. So in when we use the geosynthetic material as a filter, separation, a separator, or as a drainage purpose, then we some characteristics should be uh, known for this geosynthetic material. Then only we can use of this geosynthetic different geosynthetic uh, material for this purpose, like filtration, separation, and drainage. So these are, first one is piping resistant. So for piping resistant, that means piping means the flow flow of soil particle with water. So due to this piping, uh, this is mostly used created below the uh, dam. So due to the seepage, and due to by this way, one for a given after a given time, there may be collapse of the dam due to this piping. So for this piping resistance, we need to uh, check the apparent opening size. That because it is mostly used for the retention of the soil. So we know that when we use the geotextile, or sorry, geosynthetics material, there is maybe due to the construction of creation of these different types, there may be pore space in between this geosynthetic material, and this pore space is called, or we can say opening phase in this geosynthetic material. And this opening phase is called apparent opening size. Then permeability. To address the permeability, we need to check the flow capacity and clogging potential of the geosynthetic material. So to maintain the permeability in between the geosynthetic material, we can address or we can check the flow capacity of this or clogging potential of different types of geosynthetic material. Then only we can use as a for permeability purpose. Then strength and durability purpose. For strength and durability purpose, we need to check the grab resistance and also the puncture strength. So we know that grab resistance means the strength or crushing tensile strength of this synthetic material, and puncture strength means by needle effect, uh, puncturing failure of this geosynthetic material. So we we need to check these two types of uh, these two types of uh, resistance or strength when you use as a strength and durability purpose of this geosynthetic material. Now we come to function of this geosynthetic material or protection. And by names we can address that we bear some, or we can say we protect some structure from another physical or chemical uh, forces. So then we use this bearing, a bearer, or we can say protector. So as a it is said that isolating one material from another. The most frequent use of this function is in inland landfills where impermeable lining prevent contamination of soil. Preventing or limiting localized damage to an adjacent material, usually a geomembrane used to line a lagoon or landfill. Thick textile pavement prevent puncture or excessive strain in the membrane. So this geo barrier and protection as a protector, using the material as a barrier and protection, mostly used to separate two materials, and mostly use and it is mostly for prevent the contamination of the surrounding soil due to some hazardous chemicals from some hazardous chemicals. So and also it is also preventing or limiting the localized damage also from the existing material, and mostly use geomembrane as a geosynthetic material, and also sometimes use thick geotextile pavement this textile to prevent the puncture and excessive strain of this membrane. We you see the figure also. There's the textile as a barrier. The different way and different geosynthetic material are used for this barrier. So for barrier, geosynthetic clay liner also used. For separator, geosynthetic geotextile used. For drainage, geonet used. For barrier, again geomembrane used. Then also compacted soil liner also used as a barrier. Then drainage, geocomposite also used. Protector, for protection, geotextile also used. And these are the different way figure. These are there are different way we can use this uh, geo geosynthetic material as a barrier, or we can say separator, drainage, and filtration also. So by one figure, we can see the different way we can use this geosynthetic material. Now we can use this geosynthetic material as a control the erosion also. So protecting and reinforcing the slope and drainage channels from corrosive erosive agent, allowing the establishment of the vegetational cover. So by this by this geosynthetic material, we can also protect or reinforcing the slope and drainage channel. And you see the figure, if, three different way we can use. And also you can use about this uh, arrangement vegetation also. So you see that first one is slope facing protected by erosion mat. So geomat is used to protect the slope face, and also over this we can use vegetation also. Then second one is slope facing stabilized by wrapped around geogrid. So by wrapping one layer by one after another, one layer, second layer, two layer, three layer, like that, we can use or protect the slope facing, stabilize the slope facing, and then also can we use vegetable uh, uh, cover also. Then third one is slope or wall facing stabilized by welded wire basket and wrapped around the geogrid. So by two ways, this third one is created. Welded wire uh, basket, geogrid, and wrapped around geogrid also we can use, and one to and protect the wall or face slope of the face. Stabilize this, and over this also we can use the vegetation cover. Then geosynthetics in roads and pavements. So I think before start this we can take a break. Then after we start again and continue our today's session and discussing further. So now we can take 5 minutes break. After that, we start again. So please stay on the line. I will be joining again after 5 minutes. So please stay on the line. So again, continue our session. So I'm sharing my presentation. Please wait. So let's start our session again. So we discuss till now we're discussing about the different type of geosynthetics material and discussing the different function of geosynthetic material. And we're discussing the geosynthetic material, the application of geosynthetic material in different way. So here first one is geosynthetics used in road and pavement. So the geosynthetic material is used to stabilize and separate the subgrade. Also used for base reinforcement and overlay stress absorption and overlay stress. So different way we can use geosynthetic material for pavement to use as a stabilize the subgrade, also reinforce the base course, then stress absorption also we can use. Then subgrade separation in embankment, road embankment is a subgrade separation. So separation referred to the ability of geosynthetics to provide and maintain the physical separation between the base course aggregate and the underlying fine grain aggregate. It does prevent mixing of two dissimilar material where mixing is caused by mechanical action generally induced by construction and operation traffic. The ingress of fine by as little as 10% by weight result in reduction of the strength by more than 80%. So we use to increase the strength of the subgrade uh, material by when we by using as a separator of geosynthetic material. And we know that here it is given one point is noted here that by mixing of fines 10%, we the reduction of the strength is more than 80%. So it is important to separate the coarse aggregate with the fine aggregate uh, because we if we mix with the fine aggregate then the and due to the fines the reduction of strength is more, so strength is more, so we can separate each material. And this and also it does prevent the mixing of the two dissimilar material by mixing is caused generally due to the caused by the operation of the construction. And you can see there is one figure given that without a geosynthetic material as a separator, the coarse grade that is used for strengthening purpose of the pavement with the fine soil, which is as a uh, subgrade in subgrade, and due to this, the strength of the pavement is reduced. And you can see this there is a bend due to the operation of traffic. So, but when we apply this geosynthetic material as a separator, we can clearly see that the fine aggregate and coarse aggregate is separated by the member. And we know that this coarse aggregate give the strength of the pavement so it can easily take uh, the load which is coming from the wheel. So by this way we can strengthen the subgrade also. Then subgrade stabilization, used as a stabilization. Geometry material used as a subgrade stabilization. Stabilization of weak subgrade entails the containment and mechanically a interlocking of the aggregates within the uh, apertures of the geosynthetic to increase the bearing capacity. So by interlocking, confining the aggregate uh, when we apply the geosynthetic material and increase the as well as increase the bearing capacity. The three important function of uh, this of reinforcement is lateral restraint is the lateral interaction between the aggregate and the geosynthetic. The presence of the geosynthetic creates the pressure that improves the strength and stiffness of the root structure. The membrane action is the ability of the geosynthetic material to reduce spread stress arising from the weak subgrade. Additionally, when a geograde is involved, a third function is to be described. Then this geogrid enhance the load distribution aggregate. So these are the function, important function when geogrid used as a reinforcement to stabilize the subgrade soil. That means by lateral restraint also, by membrane action also, by load distribution. And you see that one schematic diagram also shown here that due to the full load, the there is depression after the load, and due to the geosynthetic material, when reaction is resistance is below the and there is maintain equilibrium after that, and we resist the wheel load due to the membrane tension, also due to the vertical load, vertical reaction. Then already discussed this. Then geosynthetic material as a base reinforce, base reinforcement. We we know that the pavement is the thickness of the pavement is divided into a subcourse, base course, a base course, like that way. Now we discuss the base reinforcement when we use geosynthetic material. So base reinforcement is achieved through uh, lateral restraint. That means we laterally confine the base uh, material, then the strength of the base is increased. With the addition of an appropriate geosynthetic, the geosynthetic aggregate system gains stiffness. That means one arrangement is created. That means soil geosynthetic aggregate. Due to the application of the geosynthetic, uh, and over this we can put soil and aggregate. One system, stiff system is created to this is called soil geosynthetic aggregate. The Stephen soil geosynthetic aggregate system provide the following structural benefits. These are preventing lateral spreading of the base, increasing confinement and thus stiffness of the base, improving vertical stress distribution on the subgrade, reducing shear stress in concrete. So these are the benefits when we due to the creation of the Stephen soil geosynthetic aggregate when we apply the geosynthetic material to improve the base reinforcement. And we can see that I already discussed this figure that without geosynthetic material as a reinforcement, the load is concentrated in one particular location. Due to this, the stress created at this location is higher, so there may be chance to fail this section. So we can use this as a reinforcement, and due to this, the load distribution is now taken place in wider area. So and there the stress also creation of the stress also get may reduce, and possibility of failure may also reduce. Then overlay stress absorption. So a geosynthetic interlayer can be placed over the distressed pavement on or within the overlay to create an overlay system. The geosynthetic interlayer can contribute to the life of the overlay via stress absorption, strain relief, and provision of the tensile strength. A stress relieving interlayer retards the development of reflect cracked stress by the pavement. Uh, it also waterproof the pavement so that when cracking does occur, water ingress cannot worsen the situation. So this material used for repairing purpose. You can say mostly for repairing of the road. There may be one portion of the road get may damage, and over then we use this geosynthetic material and over then aggregate and compacted the material and again the build the pavement. And due to this application, the crack may not be developed further, and the formation of crack may also get prevented, and excess stress and strain also get may relieved. And it also use by this way we also use for as a waterproof proof. That means it can also resist the water also you see that one figure is given here means when we without synthetic one is with geosynthetic. So first without geosynthetic there may be developed crack due to if we use the layer coating layer of the pavement, we can reduce the propagation of the crack due to the road. And this geosynthetic use as a waterproofing of this pavement, and that means it cannot allow the water to seepage or inflate into the base material or subgrade material. By this way we can prevent the failure of the uh, level of the surface road. Now, overlay reinforcement. Reinforcement occurring when an overlay is able to contribute significant tensile strength to the pavement system. The reinforcement attempts to prevent the cracked old pavement from moving and holding cracks throughout. That means there may be possibility to crack the surface due to old surface due to the generation of tensile forces. And this may be happening due to traffic load or thermal stress. And we can use this geosynthetic material as a reinforcement over the surface, and there may we can reduce the possibility of cracks due to generation of tensile force. The benefit of this there include the overlay thickness also. We know that due to the application, the strength also increase. We know one as know that if strength increase, the thickness of the pavement surface also reduce. So by this way, we indirectly reduce the pavement thickness. Then delaying the appearance of reflective plane. So we already discussed that due to the application of the geosynthetic material, the crack which is generated below the surface, or you can say it may reduce. Then lengthening the useful life of the overlay. So we can increase the lifespan of the pavement surface. And one figure is also given here that a cross section of the road can say mostly. That means and different at different section we use different types of geosynthetic material for different function. That means as there we know that the road cross section is divided by subgrade, subbase, base course, and also some one pavement base course coating. So below for drainage purpose and filtration purpose, and between subgrade and subbase geosynthetic use, and also same reason we use for subbase and base course, uh, in between subbase and base course. And there we can use for air purpose, and also use for stiffening purpose also, reinforcing purpose also, and also use as a separator also. Then another way we can use this geosynthetic as a drainage of the subgrade. That means subgrade dewatering. Soil can interfere with the stability of the subgrade soil. For instance, some clay soil can swell or sink as the density decrease. That's why geosynthetic material become useless in subgrade drainage application. Commonly, geotextile are being used in lieu of select the grades of sand because they are less expensive, provide more consistent properties, and are much easier to install. So, due to the subgrade, the stability of the soil may be reduced, and that most of the case this may happen due to the presence of the clay, because clay is soil and sinks very quickly in the presence of the water. To reduce this, we increase the so to reduce this, we use geosynthetic material, mostly geotextile material with uh, in lieu of sand. Geotextile with sand. Why? Because it may more consistent properties. It has more consistent and easier to install. Then drainage, road-based drainage. Then we use base introduction of the geotextile into drainage application has enhanced the economical application of, of blanket and trench drain under the adjacent to the pavement structure respectively. The excellent filtration and separation characteristic associated with filtration geotextile permits the use of a single layer open graded base or trench aggregate enveloped uh, enveloped in a geotextile. So by this arrangement, we can also use geotextile on pavement surface. Mostly it is economical and also built to the trench range and blanket range adjacent to the pavement. And it has more function also apply. One is filtration and another one is separation. Sorry for that. Now drainage for structure drainage. It has become customary to place a vertical blanket of impervious sand or gravel behind the retaining wall for protection against the hydrostatic pressure. One of the best way to assure effective aggregate drainage is to sandwich and is is to sandwich an aggregate layer within layers of filtration geotextile. The inclusion of a perforated drain pipe that collects and discharges seepage will increase the drain's efficiency. Backfill is placed directly against the drain. So this geotextile, or sometimes, or we say the geosynthetic material, precisely we can call it geotextile. It is used to drainage for structure also. That means mostly used for it is for retaining wall to reduce the hydrostatic pressure uh, behind the retaining wall. So and most effective use when it is sandwich and aggregate layer within layers of filtration geotextile. So one schematic diagram is given of the surface drain to cut the surface runoff. So we see that one slope is given here, and behind this slope, one surface drain is given, and at the depth of the below the surface drain, one arrangement is created to collect the water, and this mostly the surface runoff, and mostly this water is drained out uh, by a perforated pipe, porous pipe. And due to this arrangement, the groundwater table is reduced. You can see that one line is joining, groundwater table line is joining to the this drain by an parabolic shape. Now, geosynthetic erosion and slope protection. It means you can use this as a slope protection also, and also as a control the erosion. Slope protection, channel protection, and coastal protection. Three way we can use this geosynthetic material to protect the slope. And we see the schematic diagram also given at the bank of any river. We apply the geosynthetic material to reduce the erosion of this bank and protect uh, area which is behind the river or synthetics in system. It is used as a envelopment over soft foundation, reinforced steepened slope, mechanically stabilize earth. So these are the different way we can use geosynthetics to stabilize the slope. One means here it is. You can see that this figure is not clear very well. So please try to understand. Uh, we see that we can stabilize the slope by using as a reinforcement. So we use this. Sorry, yes. Okay. Use this geosynthetic material as a to create the earthen slope or reinforced slope. One layer after one layer we create by this geosynthetic material, and first we laid one geosynthetic material. Over this we put some good material, strengthened material, like mixture of gravel and wood sand, and compacted it and wrapped this and folded it, and one layer is created, and again the same way another layer is created, and then we protect the face due to temporary framework, and by this way we can create some strong reinforcement to protect this bank of the river. You see that one figure is also practical figure, arrangement figure also given here. Now we're discussing the benefits by using the geosynthetics. What are the benefits while using the geosynthetics material? It enhances the geotechnical properties, engineering properties, including bearing capacity, structural uh, sorry. Sorry for that. There may be um okay. Hello. So we're discussing the benefits using geosynthetics. So it enhances the geotechnical properties, including the bearing capacity, structural stability, shear strength, and deformation resistance, and achievement of higher resilient elastic modular stiffness. is the range of permissible linear, elastic, and lateral strain. It improves the subgrade strength, deformation resistance through stress mobilization, expanded distribution, as well as further tension curve. By spreading and distributing the imparted stress over a wider area of the foundation, geosynthetic may be improving the foundation and subgrade in a mode that is analogous to stage loading consolidation. Enhance structural performance resulting from increased resistance to deformation, prevention of the migration of the inferior material into the upper pavement layer. This result significant improvement in the structural performance and elongation uh, of the lifespans of the pavement surface. Many other benefits like cost and time saving increase the lifespan, better performance, lesser maintenance, and environmental impact, less use materials and erosion control. Now we discuss the another topic is mechanically stabilized earth wall. So now we discussing the mechanically stabilized earth wall. What is its basic concept and how it is? What is the mechanism and benefits like that? So you see that one schematic figure is given. That means we can use to create some wall like retaining wall by this geosynthetic material through different arrangement, and we see that one retaining wall is created. We also call it mechanically stabilized retaining wall. One retaining wall, it is created by reinforced field material, and one facing is given. Also, drainage path is also given to retain the soil, and it is built on some foundation soil. That means some good soil. So the basic concept is consist wall facing more than 70-degree angle, reinforced field, retained soil, and foundation soil and drainage layer behind the wall facing is show as shown in figure. Wall facing can be geosynthetic, wrapped around stone field, gabion basket, modular block, and concrete panel. That means this facing of wall facing is created by this geosynthetic wrap around stone field, gabion. We can use to create this facing. Modular block also used to create this facing. Then concrete panel also used to create this facing. The reinforcement can be geosynthetic reinforcement, geogrid or woven geotextile or metallic reinforcement, which provides tensile resistance to minimize the effective field movement and maintain the stability of the wall. The reinforcement and compaction reinforcement alternate. Each reinforcement is connected to wall face by a mechanically contractor. Now we discuss the suitability. The mechanically stabilized earthen walls are mostly suitable in bridge approaches when large elevation changes are needed to connect the road to bridge. The biggest advantage of mechanically stabilized earthen wall is that it can be built in less land space as compared to the with the slopes. Backfill should be free draining granular material with a plasticity index less than 6. If the foundation soil is plastic, it should be removed, improved or considered integrated stability enhancers. Because of their flexibility, mechanically stabilized earthen walls performed well in seismic areas. So these are the different suitability when we use this mechanically stabilized earthen wall. Now we discuss the advantages and limitation of this mechanically stabilized earthen wall. First, we discuss the advantages. The mechanically stabilized earthen walls are relatively easy to build. It does not require facility, contractors, and equipment. Most they mostly are they require less right-of-way space as compared with slope. They are cost-effective, tolerant to differential settlement as compared with gravity wells. Now we discuss the limitation. The mechanically stabilized walls are often required high quality backfill material. Durability of metallic and geosynthetic reinforcement is chemically active backfill may reduce the service life. Poor drainage and global instability are two major reasons for some failed of mechanically stabilized earthen walls. In short, we can MSC wall. Now we discuss the different so and different how different way is making stabilized earthen wall. One is in external failure, it may fail by sliding, by overturning, sometimes by bearing also. In internal, it failed by rupture, pull out, and connection failure also. In local failure, it is failed by toppling or bulging. In compound failure, it failed by in the form of slope failure or slip surface, maybe partially or fully out of the reinforced zone. In global failure or deep-seated failure, this failed by in the form of slope failure. Now here it is given different failure mode. So we see that in figure five different failure mode. For these five different failure mode, five schematic diagram is shown. Now now we discuss the potential stress and tension in reinforcement. The reinforced field is divided into active and stable zone by a zone axis as shown in figure. So be, bef- we also we can say soil laning also we can discuss this. Yes, soil nailing. Encourage you also can discuss this that the when the slope is failed or returning backfill material is failed, two zone is created. One is active zone, another zone is stable zone. And we know that in active zone the soil is totally failed. So as stable zone we use uh, to resist the failure zone. So due to this failure, one slip surface also created. The active zone tends to slide down under self-weight, while the reinforced anchor in the stable zone provide tensile resistance to stabilize the slip. Now, one active earth pressure theory is given. We also this type of arrangement is discussed in our soil mechanics class. We at in chapter active earth pressure and retaining one. We have this type of uh, arrangement. So same way we also find out the earth pressure coefficient or in active earth pressure. So in active earth pressure theory, the analysis of geosynthetic reinforced earth wall is mainly based on active earth pressure theory, Rankine theory. We use Rankine or Coulomb's theory. So one arrangement of the reinforced and see that the active earth pressure is given here is KAE gamma 1 H1 square by 2, and the action of this uh, is it is acted at a depth from the uh, below uh, from the to depth of height of h by 3, and the wall facing is inclined at an angle of omega, and the backfill surface is also inclined at an angle of beta, and it is and width of facing is given b and width of the wall is given l, and at below it is one friction force is given r or lateral force given rbs, and all also reaction force is given and weight of the wall reinforced material also given w1. So by this way we can find out active earth pressure coefficient uh, due to this arrangement, which is equal to cos square phi t subscript plus omega divided by cos square omega cos omega minus delta into 1 plus root over sin phi theta plus delta sin phi theta minus beta cos omega plus whole square, and omega is the wall facing, that is slope angle of the wall, and beta is the top slope angle, phi t is the friction angle of the retained soil, and delta is the inclined line. Now, if uh, one there is two types of retaining wall is given. One is created by solid material, another one is created by solid material. That means rod inclusion like that way. So for these two type of we have different field mechanism also created. We can see that the pressure distribution diagram for geosynthetic material is at top it is 0, there is some value that is KAI gamma H uh, H by 2 like that way, and for material at top is 0 and at bottom is 0, and there is the width is 0.3, and here some conclusion some points given that us to suggest that 2012 suggests that delta is equal to beta, and beta is less than equal to two-third of minimum of phi r or phi t. Fire is the friction angle of the reinforced soil. When the better angle is small, less than 10 degree, Rankine coefficient earth pressure may used. That means Ksc is equal to, that means omega is equal to 0. So put omega is 0 in previous equation and we get this formula. Then it is said that the potential failure plane which divides the active and stable zone is defined as an inclination angle psi. When the wall beta is small, less than 10 degree, Rankine's theory can be used to determine the psi is equal to 45 degree plus phi r by 2. So these are the few uh, consideration to find out the active earth pressure coefficient. Then on the formula it is given that active lateral earth pressure applied on the back of the wall facing can be induced by the active earth pressure and the structure on the top of the wall for simplification and approximation. Sorry, suggests that Astor suggests that an average vertical stress on the top of the wall acting as a slope to represent an actual slope. In addition, AS2 2012 assumes a smooth interface between the wall facing and the field so that the equation previously shown can be simplified. And the passive earth pressure is equal to Ki is equal to cos square omega plus phi r and cos cube omega plus sin phi r divided by omega cos omega whole square. When the wall better angle is less than 10 degree, the coefficient of internal active earth pressure will be modified to Ki plus phi by 2. So the better and lateral earth pressure coefficient ratio depends on the depth below the top of the wall as shown in the figure. So this figure is shown the variation of the earth pressure coefficient with the depth, and you see that at the top the coefficient is more, and at bottom it is reduced to 1 or sometimes 1.5. For metallic reinforcement, the lateral earth pressure coefficient decreases with the depth down to 6 meter and then increase with the depth. For geosynthetic reinforcement, the coefficient is constant with the depth and equal to Ki. So these are the few points which describe the variation of the lateral earth pressure coefficient with depth. We discussed the different design requirements for this mechanically stabilized wall. So it is discussed that it is fulfilled requirements is it is fulfilled by providing a reasonable value of factor or against failure by different modes. The recommended value of factor of safety suggests the design course summarized given below. For external failure, the modes of failures are sliding, overturning, and bearing capacity. We already discussed this. And for this, the factor of safety for sliding is greater than 1.5. For overturning, it is greater than 2. And for bearing capacity, it is greater than 2 to 2.5. And these are the common factor of safety for any type of slope or retaining wall uh, failed by the external uh, modes. Now for internal, which is failed by mostly failed by the geosynthetic rupture or by pull out and connection. For geosynthetic rupture, the factor of safety is greater than 1.5, and for pull out it is greater than 1.5 with embedment, and the connection factor of safety is greater than 1.5. Overall, deep-seated factor of safety is for overall, which is failed by deep-seated and settlement and differential settlement. For deep-seated, the factor of safety is greater than 1, and for differential and settlement, total settlement, the factor of safety is greater than the project dependent. For static, the factor of safety is greater than 75% of the static factor of safety for all failure mode. Now, post diagram the analysis is given that it is, we can say free body diagram we can sometimes call. So this arrangement is given. So all the forces are shown in this figure. Active earth pressure and below the reaction force, sliding friction force, weight of the soil, and by this way we find out the active earth pressure. And for base sliding, the factor of safety is given here is that the ratio of the sliding resistance force by to the sliding driving force. So the to find out the sliding resistance force, CVL plus W1 plus W2 plus PAV in 10 delta P, where CV here it is cohesion, L is the length of the failure surface, W1 W2 is the weight of the PV, A is the pressure, and delta is the oil friction, the internal friction between the wall and soil. Now overturning, which is the ratio of the resisting moment to the driving moment, and to find out this, you from the figure we find out that W1 x1 plus W2 x2 into plus PAV into L divided by PA ZA. By this formula, we find out the factor safety for overturning. And here pressure diagram is given uh, uh, to is created during the uh, application of the force. And by this way, we also find out the eccentricity during due to the bearing capacity failure. What is the maximum eccentricity to maintain the compression at the below when no non-correction of the tensile stress, and by this formula we can E is equal to L by 2 minus W1 plus into X1 plus W2 by S2 plus PV. But that means by this formula we can easily find out the E, and what is the maximum eccentricity we can find out. And we know that between this eccentricity there is may not be possibility to develop any tension at the base. We find out easily. Also one example also given, which is given here. It is CF NC plus zero point 0.5 L minus L 2E. By this formula, we also find out the ultimate bearing capacity, and then we find out the factor of safety against the bearing capacity failure, and we know that is ultimate bearing capacity by PV, and PV also find out above formula. And due to this all formula, we find out the factor of safety against bearing capacity failure. Now we find out one formula is given, that is Ti max is equal to half into PAI plus PAI plus 1 into SVI, where PAI is the active earth pressure at a different layer 1, 2, 3, and SVI is the spacing between two reinforcement, and AV is the maximum tensile force for this reinforcement. And again, another arrangement is given for different failure zone mode. Uh, First one is for geosynthetic, second one is for metallic failure use. and again two formula is given for to find out the factor of safety. One is for pull out, another one is for tensile force, and these two formula is used to find out the factor of safety. And again, to find out the pull out, one formula is given, that is 2f into alpha c rc sigma, or also you can say it is 2ci rc sigma z la tan phi. By this formula, we find out the total pull out force, and these are, and okay. Now, by this way, we find out the different factor of safety. So now, so so now we discussing all. I think we discussing the all or five lectures um, in this week by this PPT, and we one course is remaining for this geosynthetic geosynthetic material, and also for our ground course. So now we stop. I stop here and meet again in the next week, which will be our last week, week 12. And good night, everyone. It is already evening here. Um, attend next week class. It will be very important for your exam purpose. And, and now I stop here. So good soon. I'm